Learning objectives. At the end of this topic, you will be able to explain the classification of elements, analyze the achievements and limitations of Mendeleevs periodic table, know the evolution of modern periodic table, analyze the position of elements and trends in modern periodic table, analyze the similarities or dissimilarities of modern periodic table with Mendeleevs periodic table. Introduction. Meena and her grandmother are having tea. You have learned that matter around us is present in the form of elements, compounds, and mixtures, and the elements contain atoms of only one type. Do you know how many elements are known till date?
100.
At present, 118 elements are known to us. All these have different properties. Out of these 118, only 98 are naturally occurring. As different elements were being discovered, scientists gathered more and more information about the properties of these elements. They found it difficult to organize all that was known about the elements. They started looking for some pattern in their properties, on the basis of which they could study such a large number of elements with ease.
Yes, Grandma.
We have been learning how various things or living beings can be classified on the basis of their properties. Even in other situations, we come across instances of organization based on some properties. Can you give me an example?
In a shop, soaps are kept together at one place while biscuits are kept together elsewhere. Even among soaps, bathing soaps are stacked separately from washing soaps.
Right. Similarly, scientists made several attempts to classify elements according to their properties and obtain an orderly arrangement out of chaos. The earliest attempt to classify the elements resulted in grouping the then known elements as metals and non-metals. Later, further classifications were tried out as our knowledge of elements and their properties increased. Let me tell you more about that in detail. Making order out of chaos. Early attempts at the classification of elements. Dobereiner's Triads. In the year 1817, Johann Wolfgang Dobereiner, a German chemist, tried to arrange the elements with similar properties into groups. He identified some groups having 3 elements each, so he called these groups triads. Dobereiner showed that when the 3 elements in a triad were written in the order of increasing atomic masses, the atomic mass of the middle element was roughly the average of the atomic masses of the other 2 elements. For example, take the triad consisting of lithium, Li, sodium, Na, and potassium, K, with the respective atomic masses 6.9, 23.0, and 39.0. These elements are arranged downwards in the order of increasing atomic masses. You will find that groups B and C form Dobereiner's triads. Dobereiner could identify only 3 triads from the elements known at that time. Newland's law of octaves. The attempts of Dobereiner encouraged other chemists to correlate the properties of elements with their atomic masses. In 1866, John Newlands, an English scientist, arranged known elements in the order of increasing atomic masses. He started with the element having the lowest atomic mass, hydrogen, and ended at thorium, which was the 56th element. He found that every 8th element had properties similar to that of the first. He compared this to the octaves found in music. Therefore, he called it the law of octaves. It's known as Newland's law of octaves. In Newland's octaves, the properties of lithium and sodium were found to be the same. Sodium is the 8th element after lithium. Similarly, beryllium and magnesium resemble each other. It was found that the law of octaves was applicable only up to calcium. So after calcium, every 8th element did not possess properties similar to that of the first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in the future. But later on, several new elements were discovered whose properties did not fit into the law of octaves. In order to fit elements into his table, Newlands adjusted 2 elements in the same slot, but also put some unlike elements under the same note. Note that cobalt and nickel are in the same slot, and these are placed in the same column as fluorine, chlorine, and bromine, which have very different properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. Making order out of chaos. Mendeleevs periodic table. The main credit for classifying elements goes to Dmitry Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the early development of a periodic table of elements, wherein the elements were arranged on the basis of their fundamental property, the atomic mass, and also on the similarity of chemical properties. Let's discuss more about Mendeleev's work. When Mendeleev started his work, 63 elements were known. He examined the relationship between the atomic masses of the elements and their physical and chemical properties. Among chemical properties, Mendeleev concentrated on the compounds formed by elements with oxygen and hydrogen. He selected hydrogen and oxygen as they were very reactive and formed compounds with most elements. He then took 63 cards, and on each card he wrote down the properties of one element. He sorted out the elements with similar properties and pinned the cards together on a wall. He observed that most of the elements got a place in a periodic table and were arranged in the order of their increasing atomic masses. It was also observed that there occurs a periodic recurrence of elements with similar physical and chemical properties. On this basis, Mendeleev formulated a periodic law which states that the properties of elements are the periodic function of their atomic masses. Mendeleev's periodic table contains vertical columns called groups and horizontal rows called periods. Mendeleev's periodic table was published in a German journal in 1872. In the formula for oxides and hydrides, at the top of the columns, the letter R is used to represent any of the elements in the group. Note the way the formulae are written. For example, the hydride of carbon, CH4, is written RH4, and the oxide CO2 as RO2. Achievements of Mendeleev's periodic table. While developing the periodic table, there were a few instances where Mendeleev had to place an element with a slightly greater atomic mass before an element with a slightly lower atomic mass. The sequence was inverted so that the elements with similar properties could be grouped together. For example, cobalt, atomic mass 58.9, appeared before nickel, atomic mass 58.7. Further, Mendeleev left some gaps in his periodic table. Instead of looking upon these gaps as defects, Mendeleev boldly predicted the existence of some elements that had not been discovered at that time. Mendeleev named them by prefixing a Sanskrit numeral, Eka, 1, to the name of preceding element in the same group. For instance, scandium, gallium, and germanium, discovered later, have properties similar to Eka boron, Eka aluminum, and Eka silicon, respectively. The properties of Eka aluminum predicted by Mendeleev and those of the element gallium, which was discovered later and replaced Eka aluminum. Limitations of Mendeleev's classification. Electronic configuration of hydrogen resembles that of alkali metals. Like alkali metals, hydrogen combines with halogens, oxygen and sulfur to form compounds having similar formulae as shown. On the other hand, just like halogens, hydrogen also exists at diatomic molecules and it combines with metals and nonmetals to form covalent compounds. First limitation. No fixed position can be given to hydrogen in the periodic table. He could not assign a correct position to hydrogen in his table. Second limitation. Isotopes were discovered long after Mendeleev had proposed his periodic classification 01 elements. Isotopes were discovered long after Mendeleev had proposed his periodic classification of elements. Let's recall that isotopes of an element have similar chemical properties but different atomic masses. Thus, isotopes of all elements posed a challenge to Mendeleev's periodic law. Third limitation. The atomic masses do not increase in a regular manner in going from one element to the next. So it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements. making order out of chaos, the modern periodic table. In 1913, Henry Moseley showed that the atomic number of an element is a more fundamental property than its atomic mass. Accordingly, Mendeleevs' periodic law was modified, and atomic number was adopted as the basis of modern periodic table, and the modern periodic law can be stated as: properties of elements are a periodic function of their atomic number. Elements, when arranged in the order of increasing atomic number, Z, lead us to the classification known as the modern periodic table. Prediction of properties of elements could be made with more precision when elements were arranged on the basis of increasing atomic number. As we can see, the modern periodic table takes care of three limitations of Mendeleev's periodic table. The anomalous position of hydrogen can be discussed after we see what are the bases on which the position of an element in the modern periodic table. Position of elements in the modern periodic table. The modern periodic table has 18 vertical columns, known as groups, and 7 horizontal rows, known as periods. Let us see what decides the placing of an element in a certain group and period. You will find that all group 1 elements contain the same number of valence electrons. Similarly, you will find that the elements present in any one group have the same number of valence electrons. For example, elements fluorine, F, and chlorine, Cl, belong to group 17. Fluorine and chlorine contain same valence electrons. Hence, we can say that groups in periodic tables signify an identical outer shell electronic configuration. On the other hand, the number of shells increases as we go down the group. You will find that these elements do not have the same number of valence electrons, but they contain the same number of shells. You also observe that the number of valence shell electrons increases by 1 unit as the atomic number increases by 1 unit on moving from left to right in a period. Or we can say that atoms of different elements with the same number of occupied shells are placed in the same period. Na, Mg, Al, Si, P, S, Cl, and Ar belong to the third period of the modern periodic table, since the electrons in the atoms of these elements are filled in the K, L, and M shells. We can explain the number of elements in these periods based on how electrons are filled into various shells. We know that the maximum number of electrons that can be accommodated in a shell depends on the formula 2n square, where n is the number of the given shell from the nucleus. The position of an element in the periodic table tells us about its chemical reactivity. As you've learnt, the valence electrons determine the kind and number of bonds formed by an element. Trends in the modern periodic table. As you know, the valency of an element is determined by the number of valence electrons present in the outermost shell of its atom. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. The atomic radius of hydrogen atom is 37 pm, picometer. 1 pm is equal to 10 to the power of minus 12 m. We will see that the atomic radius decreases in moving from left to right along a period. This is due to an increase in nuclear charge, which tends to pull the electrons closer to the nucleus and reduces the size of the atom. We will see that the atomic size increases down the group. This is because new shells are being added as we go down the group. This increases the distance between the outermost electrons and the nucleus so that the atomic size increases in spite of the increase in nuclear charge. As we can see, metals like Na and Mg are towards the left-hand side of the periodic table, while non-metals like sulfur and chlorine are found on the right-hand side. In the middle, we have silicon, which is classified as a semi-metal or metalloid because it exhibits some properties of both metals and non-metals. In the modern periodic table, a zigzag line separates metals from nonmetals. The borderline elements boron, silicon, germanium, arsenic, antimony, tellurium, and polonium are intermediate in properties and are called metalloids or semi-metals. As the trends in electronegativity shows, nonmetals are found on the right side of the periodic table towards the top. These trends can also help us to predict the nature of oxides formed by the elements, because it is known to you that oxides of metals are basic and that of nonmetals are acidic in general. Summary. Let's summarize the topic. Today, we have learned that the classification of elements are made on the basis of their properties similarities. The elements were categorized as triads by Duberiner and law of octaves was given by Newlands. The elements were arranged in an increasing order of their atomic masses and according to their chemical properties by Mendeleev. The existence of some yet to be discovered elements on the basis of gaps in his periodic table were predicted by Mendeleev.